HighBridge, a division of Recorded Books, presents The Sun, a Very Short Introduction by Philip Judge, read by Patrick Lawlor. Publisher's Note: in this audio edition you will hear references to illustrations, figures, images, and tables present in the print and e-book formats of this book. Chapter 1. The Sun, Our Star. Our familiar sun. It is no surprise that our ancestors worshipped the sun. To the ancients, the sun was the dependable source of light, heat, raw energy, and life itself. For civilizations everywhere throughout time, the rising of the sun was, as a matter of daily experience, something to be wholly relied upon. Time itself was marked by the sun's motions. No aspect of life was unaffected by the sun. The sun's steady brightness and regular motion marked seasons for planting, harvesting, lambing, and calving. Civilizations worldwide honored the sun with monuments that were built to endure. The ancients experienced and documented solar eclipses. Such moments caused uncertainty and consternation, leading to awe, fear, and wonder. The temporary darkness during total eclipses served perhaps to remind humanity that the heavens could not entirely be taken for granted. In some cultures, eclipses took on deep significance with important political consequences. In the Chinese Bamboo Annals, dating from circa 300 BCE, an eclipse of 1059 BCE is recorded as having triggered actions leading to the fall of the Shang and rise of the Zhou dynasties. Yet in the hustle and bustle of our modern lives, like a devoted spouse, the sun is all too readily taken for granted. A stockbroker might promise that a share's price will increase as sure as the sun will rise tomorrow. We have become accustomed to our star. Perhaps our nonchalant acceptance arises from our modern understanding of the mechanics of the solar system, developed first by Isaac Newton, 1642 to 1727, who had synthesized theories of motion and gravity based upon astronomical observations, and calculations of Nicholas Copernicus, 1473 to 1543, Tycho Brahe, 1546 to 1601, Johannes Kepler, 1571 to 1630, and Galileo Galilei, 1564 to 1642. We know that the sun will rise tomorrow owing to Earth's rotation, a consequence of Newton's laws of motion. Our 20th century knowledge of nuclear processes and energy transport gives us faith that it will also shine. We can easily forget that the sun is the source of almost all energy that we can readily use, from fossil fuels, winds, and waves to solar panels. So long as the workings of the universe are the same tomorrow as they are today, we can live our lives simply knowing that the sun will be our faithful companion. This, a modern act of faith, is based upon the same experiences as the ancients. For if this had not been the case over the almost unthinkably long time of several eons, the large and intricate forms of life on Earth, such as you and I, could not have come into being. Unlike some acts of faith, modern understanding of nature, an endeavor called science, is supported by a vast collection of evidence and centuries of rejection of unsatisfactory pictures, weeded out by experience and by pitting ideas against observations. The result of such endeavors in understanding the sun is summarized in Figure 1, which will serve as a reference for the rest of this chapter. This is a book about the science, the workings of the sun, about solar physics. The importance of the sun. Why is the sun important? It is, after all, a nondescript star, differing little from billions in the Milky Way galaxy. It is a star of typical mass, typical color and luminosity, a middle-aged star. It is of spectral type G in the range O, B, A, F, G, K, and M. That is a sequence of decreasing mass and temperature. Yet the Sun is special and of interest simply because of our proximity to it. From Earth's orbit, the Sun is over 270,000 times closer than Alpha Centauri A, the nearest nighttime star that is otherwise sun-like. Our closeness allows us to observe, measure, and document its behavior in detail. Table 1 lists some physical properties of the Sun as well as its classification among the stars. The notation G2 in the spectral type refers to the Sun's color and approximate temperature in the stellar O through M sequence, running for G-type stars from G0 to G8. The V denotes the size of the star, or its luminosity class among the stars. It classifies the Sun as a normal dwarf star, currently on the main sequence. Table 1. Some basic properties of the Sun. Mass: 2 × 10⁻³ kilograms. Radius: 700,000 kilometers. Distance: 150 million kilometers is equivalent to 1 AU. Luminosity: 4 × 10⁻26 watts. Irradiance at Earth: 1.365 kilowatts per meter to the -2nd power. Average rotation period 27 days. Stellar spectral type G2V. The irradiance at Earth is the amount of radiative power received across 1 meter square at Earth's orbit over 1 kilowatt per meter square. Not only does this make the Earth habitable with a comfortable average temperature of 14 Celsius, but if we could convert 100% of the radiative power of the Sun collected by an area of just 0.4 meters square into electrical power, it would satisfy the current energy needs of an average household in the UK continuously. The Sun's proximity also makes it important as a laboratory for studying basic physical phenomena that can occur under conditions totally unreachable in our laboratories. Solar studies inform us of nature operating on the enormous scales encountered across the universe. It exhibits remarkable phenomena that we take for granted, such as sunspots, the corona, flares, the solar wind, and coronal mass ejections, CMEs, to be discussed next. Similar phenomena occur in different guises in many astrophysical plasmas, in which plasma motions and magnetic fields interact. Yet we could not anticipate any of these phenomena from first principles. The Sun is thus a proving ground where we can test theories of magnetized plasmas, of importance also in our quest to find safe power from nuclear fusion. Using the Sun as our laboratory, we can try new measurement techniques in astronomy and pit them against theories and models in our quest to understand the entire universe. The Sun and stars are in a different state of matter than the solids, liquids, and gases with which we are familiar. They consist of ionized particles that are in the plasma state. Just as it takes energy to break chemical bonds to make a liquid from a solid, melting, and a gas from a liquid, evaporation, the addition of considerably more energy separates the electrons from their atomic nuclei to form an electron-ion plasma. Plasmas are the natural state of matter when the energy per particle, proportional to their temperature, is high enough to keep electrons separated from their parent atoms. Most objects in astronomy bright enough to be seen are in the plasma state. Along with charged particles, plasmas are flooded with light that is emitted and absorbed by the moving charges. We can consider a plasma to consist of electrons, ions, and photons, the latter being small quanta of light. As we will hear, the large energy densities required to make these astronomical plasmas arise naturally in astronomy from the inexorable effects of gravity after matter condensed out of the raw energy of the Big Bang. The defining property of plasma is that it is made up of free charges, electrons and ions. Electrical charges were familiar to philosophers from 600 BCE, but its effects were first experimentally quantified far later by Charles-Augustin de Coulomb, 1736 to 1806. He developed the concept of an electric field in which each electrical charge endows the space around it with a force that acts on other charges. The lines of force begin and end at electrical charges. The freedom of charged particles in a plasma to move between random collisions means that the plasma is an excellent electrical conductor. Just as the electrons easily move along household copper wires to form a current, an orderly relative motion of free electrons and ions in a plasma constitutes an electric current inside the plasma itself. The sun's corona conducts electricity like copper, but plasma is more like a fluid than a wire. Mercury is familiar to us as a liquid on Earth's surface, with a conductive efficiency of about 1/50th of copper. And indeed, laboratory experiments with liquid metals have helped inform us about the workings of the sun. In contrast, seawater supports electrical currents carried by electrons removed from and attached to ions of sodium and chlorine in solution. These heavier ions are far less mobile than electrons, and so seawater has about 1/10,000,000th of the conductive efficiency of copper. Both magnetic and electric fields exist in the Earth's atmosphere, allowing birds to navigate and sparks to occur through lightning. But in the sun, the electrons are so mobile that any large-scale electric fields are almost immediately shorted out, just as in a copper wire. Any magnetic fields survive intact against shortouts because no one has found evidence for any magnetic charges called magnetic monopoles. Based upon historic experiments by Coulomb, Jean-Baptiste Biot, 1774 to 1862, Félix Savart, 1791 to 1841, André-Marie Ampère, 1775 to 1836, and Michael Faraday, 1791 to 1867, James Clerk Maxwell, 1831 to 79, unified electricity with magnetism. Experiments show that magnetic fields are generated not by monopoles, but by electric currents, that is, the relative motion of positive and negative charges. In turn, magnetic fields exert forces only when charges and field are in relative motion. In the absence of monopoles, magnetic field lines have no beginning and no end. Only two kinds of magnetic field lines can satisfy this condition. One is that the magnetic field lines make up complete loops, such as those threading through and around bar magnets. The other kind is in an ergodic state, where field lines go on forever throughout the universe. The former concept is most useful for discussing a finite object like the sun. Electric and magnetic charges. While electric fields begin and end at electric charges, magnetic fields circulate around electric currents. Maxwell's theory is entirely symmetric with regard to electric and magnetic fields, with just one exception. It contains no magnetic charges. So magnetic lines of force have no beginning, no end. If magnetic charges were abundant, they too would in principle move, just like the electrons, to short out their fields. But this is not the case. In an elegant book, Conversations on Magnetic and Electric Fields in the Cosmos, Eugene Parker, 1927 to present, concludes that abundant magnetic charges, monopoles, would short out any magnetic fields within plasmas. But in their apparent absence in our universe, we see that a body of plasma like the Sun can sustain large-scale magnetic fields, but not large-scale electric fields. The Sun is important also because it is not quite as benign as some might believe. The solar corona emits a steady stream of ultraviolet, UV, and X radiation, as well as plasma emerging as the solar wind. The interactions between dense solar plasma beneath the visible surface and the magnetic fields that generate the corona can eject intense and unpredictable bursts of high-energy radiation, jets, plasma, and magnetic fields into interplanetary space. The Sun is a machine that converts a small but important fraction of its benign power into variable energetic radiation, magnetism, and particles. It is fair to say that today, the biggest problems in solar physics concern the dynamical interactions between solar plasma and its magnetic fields. In passing the Earth, solar outbursts disturb Earth's protective magnetic field, causing problems for electrical infrastructure, though leading to beautiful aurorae. Our increasing technology dependence makes our way of life vulnerable to sustaining damage as a result of the poorly understood workings of our otherwise friendly neighbor. There are plenty of reasons, then, why the Sun is important and worthy of further discussion. Sunlight and the Beginnings of Astrophysics. The publication in 1687 of Principia by Sir Isaac Newton is as good a place as any to mark the beginning of physics, the subject concerned with the quantitative understanding of elementary natural processes. But it was not until the 19th century that the seeds of astrophysics, concerned with the nature of remote heavenly objects as opposed to just their motions, were planted. In 1814, Joseph von Fraunhofer, 1787 to 1826, following work with prisms by Newton and William Hyde Wollaston, 1766 to 1828, in 1802, re-examined the solar spectrum. The solar light entered Fraunhofer's spectroscope through a slit, using lenses and a prism to enhance the splitting of light into constituent colors. In this way, he was able to show that the spectrum of the Sun consisted of a bright background with a large number of darker dips at particular wavelengths. In 1821, Fraunhofer developed a new spectroscope based on diffraction to achieve a stronger splitting of light, dispersing it into more than just broad constituent colors. The trick took advantage of the wave nature of light. Fraunhofer's dips, now called spectral lines, were labeled alphabetically ranging from red to violet. These lines have been commemorated on a stamp. The smoothly changing background in the stamp shows the continuous thermal solar spectrum, going from infrared, IR, on the left to UV on the right. Figure 3 shows the spectral brightness as a function of wavelength as a line plot, with colors marked showing only the continuum. The dips in the spectrum are the dark vertical lines in the lower half of the stamp. They are a persistent solar feature. Their origin remained a puzzle until breakthrough laboratory experiments were made by Robert Bunsen, 1811 to 99, and Gustav Kirchhoff, 1824 to 87. In 1860, they demonstrated that the solar dips coincided with wavelengths of bright emission seen in some flames. For example, two solar lines in the yellow region, labeled D1 and D2, appeared when sodium was introduced into the flames. The coincidence in wavelengths hinted that sodium was present on the Sun. John Dalton, 1766 to 1844, had found that matter is assembled of elements, and Bunsen and Kirchhoff had demonstrated that compounds of such elements, seen under conditions of combustion in gases, had these telltale spectral fingerprints. Soon after solar spectra were scrutinized, bright star spectra were also compared, revealing diverse sets of spectral lines. Thus began the era of modern astrophysics, the era in which we could begin to quantify the nature of astronomical bodies remote from our laboratories. For astronomers, spectral lines were the DNA of their time. Just as DNA was to set genetics on a firm and quantitative basis a century later, spectroscopy allowed astronomers to build a firm foundation for examining the structure and evolution of the universe. In fact, on occasion, this DNA of some elements was seen first not in the laboratory, but in spectra of the Sun and other astronomical objects. A third solar line, D3, was speculatively associated with a new element, helium, after it was seen in emission at a wavelength different from D1 and D2 in 1868 by Norman Lockyer, 1836 to 1920, and Edward Frankland, 1825 to 99. The intrepid Pierre Janssen, 1824 to 1907, reported the emission line earlier, during and outside of a total eclipse, but had assumed it to be sodium. It was only later that it was identified in the laboratory by chemists Père Théodore Cleve, 1840 to 1905, and Nils Abraham Langlais, 1868 to 1936, while studying the uranium ore clevite. Yet it is the second most abundant element in the universe. At the eclipse of 1869, Charles Augustus Young, 1834 to 1908, he died on the day of a total solar eclipse, and Civil War surgeon, astronomer William Harkness, 1837 to 1903, independently observed visually the green coronal line. The line's origin was unknown, and some believed it to belong to a new element, coronium. There followed a period of 70 years of debate until it was finally identified by Bengt Edlane, 1906 to 93, along with several other lines of highly ionized complex atoms. Fluids, gases, plasmas, and magnetohydrodynamics. Motions in our atmosphere are described using fluid mechanics. Solar physics uses the same description. In both cases, additional processes are added as needed, for example, cloud condensation in our atmosphere. But large-scale motions are best treated using the so-called fluid approximation. In physics, a fluid describes well-defined averages of numbers of particles over finite volumes. We speak of the number of atoms per cubic meter and their average speeds. Temperatures measure the spread of speeds of individual atoms around the local averages. Equations are solved for these averages, continuous quantities first described mathematically by Leonhard Euler, 1707 to 83. All physical processes occurring inside the small volumes, like collisions between particles, are not addressed in the fluid approach. Instead, other methods, such as kinetic theory, are brought to bear to define necessary large-scale properties, such as pressure, viscosity, and conductivities, like heat or electrical conduction, inside the fluid. Even in this case, classical mechanics describes the small-scale motions and interactions well in almost all conditions, except during the latest stages of evolution of the Sun, when quantum effects become critical. Euler's work builds on experiments and theory extending back to Archimedes. The price paid by Euler's averaging is that the formulation becomes nonlinear, leading to difficult problems such as turbulence. But this is more than worth it, for otherwise we would have to trace trajectories of an impossibly large number of interacting particles. The simplest description of solar plasma is as a magnetized fluid. This fluid can sustain large-scale magnetic fields, but not electric fields. The subject is called magnetohydrodynamics, or MHD. Over the next century, advancements in solar physics came hand in hand with several revolutionary advances in physics, including statistical mechanics, Ludwig Boltzmann, 1844 to 1906, Maxwell, the unification of electricity and magnetism by Maxwell, the birth and evolution of quantum mechanics, and Albert Einstein's 1879 to 1955 theories of relativity. In the early 1920s, Meghnad Saha, 1893 to 1956, developed an extension to the Maxwell-Boltzmann statistical theory to include the effects of quantization on the ionization state of a gas or plasma. The state of ionization describes how many electrons are bound to a given atom. Carbon, C, for example, normally has 6 electrons in orbit around the nucleus, which itself has 6 protons and usually 6 neutrons. If we remove 1 electron, we have C+, written because we only have 5 negative electrons surrounding the 6 proton charges in the nucleus, leaving a net positive charge of 1 proton. Removing another electron leads to a state of carbon labeled C2+, and so on. Each removal of an electron requires energy. Temperature measures the amount of energy in the motions of each particle in a plasma, and Saha was able to derive a new equation describing how, at each temperature and density, the ionization stages are determined. For astronomy, Saha's development proved crucial because the statistical theory of plasmas was, until then, incomplete, there being no theory that included the degrees of freedom associated with free electrons. Into the revolutionary atmosphere of physical advances of the 1920s came a remarkable student, English-born Cecilia Payne-Gaposchkin, 1900 to 79, supervised by the director of Harvard College Observatory, Harlow Shapley, 1885 to 1972. In her 1925 PhD thesis, armed with Saha's statistical theory, Payne-Gaposchkin examined the amount of the star's light that is absorbed in the spectral lines. She found that it depended critically on the state of ionization, not just the abundance of the elements. Her analysis led her to conclude that the sun was composed mostly of hydrogen. This was such a shocking result at the time that eminent physicist Henry Norris Russell, 1877 to 1957, advised that she not adhere to her findings. Initially, she described her conclusions as spurious, but her work was proven right, including by Russell himself a few years later. By the mid-1920s, the subject of astrophysics was set to explode. Our modern theory of stellar evolution, based upon Payne-Gaposchkin's work in 1925 and with the sun at stage center, is surely one of humanity's great intellectual accomplishments. Solar structure. Figure 1 sketches the overall structure of the sun. The story behind this picture is remarkable, encompassing and driving some of the giant leaps in physics made during the 20th century. The core of the sun, consisting of the energy-generating center and a region of radiative energy transport, is surrounded by the convection zone. While neither region is directly observable using light or other kinds of radiation, we believe that their basic structure is well understood. Immediately above the convection zone is the visible surface called the photosphere. It too is fairly well understood, subject to some intricacies discussed later.
Sample complete. Ready to continue?